All right, so the key is to look at this from the top, and hopefully you can see this is 1 and this is 4. The region of integration is this, okay? That's what you're trying to integrate. So the region R is that theta goes from 0 to 2 pi, as usual, but this time R only goes from 1 to 4, okay? And again, it is very circular, and this is called an annulus. And so you can find the volume to be, oh yeah, I have to write this equation here, right? What's the height at each point here? Well, in terms of, you know, I mean, what's a sphere? It's x squared plus y squared plus z squared is equal to 16, but that's r squared plus z squared is equal to 16. And because we're talking about a hemisphere, it is the square root of 16 minus r squared. Okay, that is the height at each point, r theta. So this is what you integrate. The double integral goes from 0 to 2 pi, 1 to 4, right? And you have an integrand, square root of 16 minus r squared. And then r dr d theta. Where did this r come from? We don't want this r. Yes, we do want this r. It's a part of dA. And in fact, you should be very thankful for the existence of this r here, because that's what allows you to be able to carry out substitution, use substitution, okay? Why am I saying this? Because inside you have 16 minus r squared. If you take the derivative of that, you have to have r. Not r squared or r cubed. You just have to have, well, it's minus 2r, right? And this r is necessary. And that's why you should be thankful for this, the presence of that r, okay? Right there. And by the way, as u goes from 4 to 1, right? So u goes from 4 to 1, sorry, 1 to 4. No, u doesn't go from 1 to 4. R goes from 1 to 4. And u, well, when, when r is 1, then u is 15. Remember, it's 16 minus 1 squared. And then when r is 4, u becomes 0. Okay, so these are the new bounds you have to consider. Every time I have a new bound, I try to put in different colors. See that? Okay. And then the rest is going to be different too, because this is u to the 1/2. Oh yeah, I don't have a -2 here. Let's go ahead and put -2, okay? I wish to see -2 in front of r. And now I see it, great. So I can just write the u here. No, I can't, okay? I mean, sure, when you wish upon a star, it always shows up. At least that's what they told me at the happiest place on earth. But see, this doesn't work. I mean, -2, where did that come from? It came from nowhere. But I can compensate for that by doing this in front. All right, so now that's pretty simple, right? All right, now one thing I just personal, this is a very, very personal preference, but I never like to see a big number here and smaller number here. Okay, every time I see this, I switch around. And to switch around, of course, I have to change the sign. So I'm gonna take this away and make that into a positive integral. And then I switch the order from 0 to 15, okay? And you don't have to do it this way, my way. I just personally feel much more comfortable if that bottom number is smaller than the top number. All right, so what's the antiderivative here? It's 2, yeah, 2/3. Not pi, but u of 3/2, right? Make sure that when you differentiate this, 2/3 and 3/2 cancel. And then you integrate this from 0 to 15 and then the theta. And so at this point, you can cancel these. It's 1/3. And then, oh yeah, what do you have here? That's 15 to the 3/2 minus 0. Okay, I'll just go ahead and do that. And then you still have that integral from 0 to 2 pi of d theta, but that's just 2 pi. Okay, so the answer is 2 pi over 3, and then you have 15 to the 3/2. You can write that as 15 times the square root of 15, right? Because it's a square root of 15 cubed. That's what it is. And so that allow us to, again, you don't always have to go this far, but why not make the answer simpler? So the answer is 10 square root of 15 times pi. And that indeed is the volume of this hollowed, drilled out hemisphere. Okay, so that's a pretty cool problem, right? All right. And again, this is optional. You can quit and start doing your homework now, but I will do one more problem, which is very similar to one of your questions on your homework, right? So let's say you have this bowl, okay? And so here's, your X, Y, and Z axis. And this bowl, okay, so this is the surface, Z is equal to 4, right? And this is a parabola where it's Z is equal to X squared plus Y squared, right? I want you to find the volume of this bowl. Okay, now again, you can pause and set your double integral up. I haven't told you what the radius or what the region of integration is, right? That's something you have to find. And try to set this up, and you can simply solve it. I think the determination or the evaluation of the integral is simple. I think you will be more than half done when you correctly set up the integral. Right? But go ahead and try to set up the integral. Maybe you want to pause this video for a few seconds and then come back when you think you've got the right answer. All right, so the region, you have to project this onto the XY axis, XY plane, or the R theta plane, right? The region of integration will be whatever the projection of this bowl is on the XY plane, right? Since, and by the way, this is the function that you are integrating is R squared, right? And you want R squared to be equal to Z, which is 4, so R is 2, okay? So that just tells you the radius, the region of integration is the radius 2 circle centered at the origin, right? So for R, 0 has the theta goes from 0 to 2 pi, it's a complete circle, and then R goes from 0 to 2, okay? Very important for you to establish these bounds. And then the volume is, and by the way, we already have the equation here. Z is equal to, sorry, I think I messed up here. This is supposed to be just Z. Okay, so Z is R squared, and so we found the bounds. Z can be written as R squared. That's my function, right? So the volume is going to be the integral from 0 to 2 pi, integral from 0 to 2, and then the integrand, which is this function. Written in the polar language, okay? Remember, in the polar language, we speak pole or polar language. And in polar language, X and Y are not in the vocabulary. R and theta are, right? So X squared plus Y squared is translated into the new language, the polar language, as R squared, okay? And here you had dA. Well, dA in the language of the polar coordinates is R, dr, d theta. Okay, notice here I have 3 of these R's, okay? This is the part that refers to dA. R squared is your integrand, all right? So you actually have R to the 3rd, right? And if you integrate that, you get R to the 4th divided by 4. Man, you got a bunch of R's here. And then you integrate this, go ahead and substitute 0 and 2, and then all you have left to do is to integrate with respect to theta. Okay, we will do that later. But what's 2 to the 4th power? That's 16. 16 divided by 4, it's 4. And so this is just 4 times 2 pi, and that's 8 pi. I hope that's what you thought the answer was. The volume of this cup or the bowl inside of the paraboloid, circular paraboloid of radius, of height 4, radius 2, turns out to be 8 pi. Okay, so I feel like I have done more practice or more examples than in other sections. I hope you got the idea, right? And I hope you also got the message that polar double integrals are nothing to be afraid of. Okay, in fact, those are pretty nice. Okay, and so with this knowledge and the mastery of this understanding of this material, I hope you practice, and I think you will do well on your homework, and then you get this thing. And this is particularly important because later we will actually be having triple integrals using polar as a basis. Remember the cylindrical, which is very much like a polar coordinate system? Yeah, so we will have triple integrals in cylindrical coordinates, which will be very much like what we are doing in polar coordinates, all right? Okay, so have fun, and I will talk to you later. Take care. Bye.